About this space. Well, I called it y0n last time, but I'm going to switch notations. Write this for the stack. So this is the stack over z adjoin 1 over n, which assigned to a scheme S, the groupoid of pairs E.g., where E over S is an elliptic curve. And G is a gamma 0 n structure on E. So it's a closed subgroup, which is finite and flat over S, and cyclic of order n in each fiber. All right, so this is the functor of points. It sends a scheme S to this groupoid. And so last time I called that y0n, but I'm going to change notations and use this for the stack from now on, y0n for the core space, which I'm about to introduce. Okay, so last time we showed that this was a Deligne-Mumford stack. And remember what that meant was that it had an étale covered by a scheme. And the way that we found that scheme was, it was very explicit, right? You just looked at gamma p structure for p some different prime. So explicitly, if p doesn't divide n, you can let's say, y be the, you define a moduli problem, y, its functor of points, sends S to the set of isomorphism classes, E, G, P, Q, where this thing here is an elliptic curve. This is a gamma 0 p structure, gamma 0 n structure, and this is a gamma p structure. They're the basis for the p torsion. And since, if p is bigger than 2, then gamma p structures are rigid, right? There were no automorphisms. And so that means that this thing is actually going to be a scheme. So y is a scheme. And we have a map from y to m0n, which is to forget the gamma p structure. And this is our étale cover. Well, at least if p is inverted. This is a scheme over z adjoin 1 over pn. So you have to use some different, various primes p to get something that works over the full z adjoin 1 over n. And so actually, m0n is the quotient of y by the GL2 z mod p action, right? It's the quotient stack. If you remember, this is how we even constructed the schemes y of n last time for certain n's using y of 3 in added structure and then took quotients. Them both switched. Thank you. Okay. So you could also just take the scheme quotient instead of the stack quotient. So this is the quotient scheme. And this actually, so sorry, again, this is just over z join 1 over pn. You have to invert this p that you're using for y, it's auxiliary structure. Okay, so this thing is the quotient scheme, and you can show that this represents the functor, which sends the scheme S to the set, well, okay, I'll say something wrong first and then fix it. So you could consider the functor that sends the scheme S to the set of isomorphism classes in M0 n of S. Right, so this thing here, M0 n of S, is a groupoid. It's a category. And so we can take its set of isomorphism classes and actually get a set. And you can consider the functor that attaches to S this set. But actually, we talked about last time, this thing's not a sheaf, right? That's why we have to go to stacks. This thing's not actually representable. So this quotient can't represent this functor, because that functor is not a sheaf. But it represents the sheafification. And this, of course, only works over z join 1 over pn. Okay, so using different p's, you can get rid of that p and get that this thing is represented over z join 1 over n by a scheme. So the sheafification of this thing is represented by a scheme which I'm going to call M0n, not a fancy typeface, or Y0n. These are going to be synonyms. And this works over z join 1 over n. And in fact, this scheme is smooth and affine. And this is called the coarse space of the stack. Yeah. I believe so. I don't know the most fully general theorem, but I believe that in great generality they have coarse spaces. So, okay, the coarse space is nice because it's a scheme instead of a stack. So it's a more concrete object. They have the same points over an algebraically closed field. I mean, the set of isomorphism classes in this thing over an algebraically closed field is the set of points of the coarse space. But the problem with the coarse space is that there's not a universal family over it, which is why we want to use stacks in the first place. All right, so I wanted to kind of introduce this now so that, I mean, if you're not very comfortable with stacks, you can kind of just think about these schemes, and you probably don't lose all that much if you just kind of pretend that everything works. So these things are pretty close to schemes. And we'll actually need these a little later on in future lectures. Well, I mean, we want to show that this functor is representable. I'm saying that if you invert p, then this quotient represents it. And so if you use two different p's, you can get it represented over a cover of z join 1 over n. Patch them together and get it over z join 1 over n. Well, I mean, yeah, I mean, this doesn't depend on any choice, right? This is a canonical thing. So we have this canonical sheaf over z join 1 over n, and then the proof of representability is, yeah. Yes? Well, no, I mean, I'm saying if you have any stack, you can consider this functor, right? Take the isomorphisms and then sheafify it. And I'm just saying that the coarse space is the scheme that represents that if it exists. Okay. And then I was saying that on closed points, on points over an algebraic closed field, they agree. That's like, how, that's kind of a generalization of the statement that the J invariant determines the elliptic curve of an algebraically closed loop. Oh yeah, so I guess I should say the main example of this to keep in mind is that when n equals 1, this coarse space is the J line. So M0 of 1, which is the same thing as what you call M of 1, just no level structure, is A1, the J line. But this script thing is actually a stack. It's more complicated. Its fundamental group is like the profinite completion of SL2Z, so it's very interesting. All right, any questions about this? All right, so okay. Today I'm also going to talk about compactifying these moduli problems in a moduli theoretic way and extending them over Z. So those are the two other topics I want to talk about today. So first we'll do compactification. So we'll start in the level 1 case. Okay, so recall first of all what happened over C when we were doing things analytically. So we defined y of 1 in that setting as the upper half plane mod gamma 1. And that agrees with this thing, it's the J line. And so this is missing a point. And a nice way to add that point in was this construction where we did the upper half plane star, H star mod gamma 1. Where H star was the union of H and the projective Q points of the projective line. And gamma 1 acts transitively on P1Q, so you're really only adding 1 point. So P1Q mod gamma 1 is 1 point. And that's called the cusp. All right, so we want a moduli theoretic interpretation of what this means. So recall this valuative criterion for properness. So if you have some scheme that you want to test if it's proper, so let's say you have some x over c, and we should assume it's finite presentation, then finite presentation is proper if, so the idea is that you can fill in point, DVR points, right? So if A is a DVR, and K is its fraction field, then every K point of X extends uniquely to an A point. Finite presentation. Finite presentation. Okay, so this is sort of suggesting that the moduli interpretation of this additional point should somehow be related to how we fill in elliptic curves over DVRs. Maybe I should say extending elliptic curve over DVRs. And this is something that we talked about and we understand very well, right? So in particular, we have the semi-stable reduction theorem. So let's recall that. So this says that if you have an elliptic curve over some fraction field of a DVR, so A is a DVR, K is its fraction field, and E is an elliptic curve over K, then there exists some finite extension, K prime over K, and such that E extends to something with semi-stable reduction over what you'd call A prime. And semi-stable reduction means either good reduction or multiplicative. All right, so if we're thinking about this moduli space of elliptic curves, I mean, if it extends to, if it has good reduction, then it's extending to an elliptic curve over all of A, and you're not in the situation where you need to add anything to the moduli space. It's actually extending to an A point of the moduli space. But in this case, where it extends to something with multiplicative reduction, right, that's not actually in the moduli space we have so far. So this is suggesting that this case is what we need to add, the missing point, the nodal cubic, right? So that's saying that what the moduli interpretation of the cusp should be, the nodal cubic. All right, so let me make some definitions and then say a theorem which kind of says that this is the case. All right, so let's take an integer n. So then I'm going to define something called the standard n-gon. So the standard n-gon which I'll call Cn, is just the quotient of P1 times Z mod NZ, where you identify infinity in the ith copy with 0 in the I plus first copy. Yeah. That's kind of a subtle point. Well, I'll come back to that in a minute. Okay. Okay, so I mean, the picture for this is, right, you're taking P1, it's like the Riemann sphere, and you're just kind of gluing them together at points like this. Or if you think of P1 as a line instead, you would draw it like this. Yeah. So this is a nodal curve. And so that's why it's called an n-gon. Because if you draw it like this, then you actually get a polygon. And the smooth locus of this guy is just the place where you, remove these points where there's nodes. So the smooth locus is just GM times Z mod NZ. And so this is a group. And furthermore, so the group, it acts on itself by multiplication, and that action extends to an action on the full thing. And so in this action, the GM part is just fixing these singular points, and the Z mod NZ part is just kind of spinning them around. Yeah. So C1 is the nodal cubic, or P1 with these 2 points identified. It's just a nodal curve. And these bigger ones are just not reducible, not irreducible curves. Okay, and so I want to point out now that if we think of this thing as a group, Cn, that its n torsion has order n squared. And in fact, it fits into a short exact sequence like this. Right, so this mu n here is the torsion in Gm, and then the quotient is this, Z mod Nz. So this mu n is in the identity component of the smooth locus. All right, so another definition, a generalized elliptic curve. So the definition is that a generalized elliptic curve is basically an elliptic curve or one of these things. Okay, but we want to make the definition over arbitrary bases, so let me write it. So over S is a tuple consisting of E, some operation called plus, and a section 0. So where E is a proper flat family, 0 is a section, and plus is a map from the smooth locus of E times E to E, such that two conditions hold. So first is that this plus should turn the smooth locus into a group and define an action of the smooth part on the full thing. And the second condition is that the geometric fibers should be elliptic curves, or these end guns. Okay, so here's a moduli problem. So I'm going to define M1 bar. So I'm going to tell you its functor of points. So to a scheme S, it attaches the generalized elliptic curves over S, such that the fibers are either elliptic curves or one-cons. So if you think of the C points of this, right, there's a unique one-gon over the complex numbers, just the one-gon. And so the C points of this are just the elliptic curves plus this one additional point. So we've just added one additional point to the usual moduli space, which is how we wanted to compactify it. And so a theorem is that this thing is so this M1 bar is a proper smooth Deligne-Mumford stack over the integers. So the key new thing here is proper. And let me make a remark about properness. So I wrote down previously the evaluative criterion for properness for schemes. For DM stacks, it's different. So you allow yourself to make a finite extension of the DVR before you have to fill in the point. That's in the definition of properness. Otherwise, things like this wouldn't work correctly. So evaluative criterion for properness for DM stacks allows a finite extension of DVRs. And so you see, if I have some elliptic curve over some DVR, so if A is over the fraction field, so if A is a DVR, K is the fraction field, and E is some elliptic curve, right? The semi-stable reduction theorem says that I can go up to some finite extension and then fill it in so that it's either good or multiplicative reduction. And I mean, if you remember that, if you use the minimal regular model, the minimal Weierstrass model, right? When you have multiplicative reduction, the special fiber is a node. So if you go up to semi-stable reduction to where you're semi-stable and use the minimal Weierstrass model, and that will fill this in over the DVR upstairs, where the special fibers in elliptic curve are a one guy. So then we get an A prime point of M bar 1. So that's basically why it's proper. The semi-stable reduction theorem is basically equivalent to the properness of this thing. Yeah? To be smooth? No, but I mean, it means that you have an étale covered by a smooth thing. Because if you have a scheme, it's smooth if and only if it has an étale covered by a smooth thing.
Okay.
And so you just make that definition for stacks. Yeah, there's also an infinitesimal criterion. Yeah, and so that would say that you can lift things, and curves, the obstruction theory, it's unobstructed because there's no H2 for a curve. And, yeah, so you could also prove it that way, the smoothness. Any other questions? I think that's usually how it's done, but I think there are places where it becomes subtle. But my understanding of it's not very good. I think that defining properness for Artin stacks is more subtle, but I don't understand that stuff very well. All right, so this is compactifying just the problem of elliptic curves. So we want to also do it when we have level structure. Gamma 0 n structure is what we care about most. All right, so if we have a generalized elliptic curve, we can define what we mean by a gamma 0 n structure in the same way. So the gamma n structure should just be a cyclic order n subgroup inside of here. That's what I'll mean by a gamma 0 n structure. And so the definition of this M0n bar, the compactified version, I mean, it clearly should involve gamma 0 n structures on generalized elliptic curves, right? But there's a little bit of subtlety in the definition. So let me explain it. So, okay, so to explain this, I didn't actually ever talk about what the cusps of x0n look like, so let's first do that. So for the moment, let's suppose that n is prime, just to make life easier. We want to understand the cusps of x0n, just over the complex numbers, say. So the cusps of x0n, which is h star mod gamma 0n, are, well, I mean, you take P1Q and you quotient by gamma 0n, right? That's what the set of cusps is, just by definition. And it's not hard to show. I mean, this is just some set, and this set is isomorphic to P1 over Fn mod the Borel inside GL2Fn. Right, so there's a reduction map, right? If you have something in P1Q, you can clear denominators and make it in P1Z. and then you can reduce to Fn. And of course, gamma 0 n is defined as the set of matrices that reduce into G mod n. So you get a well-defined map here, and you can show that it's an isomorphism. And now here we just have the Borel acting on P1 Fn. So I mean, the way that Borel acts is by sending x to ax plus b. It's just linear maps. So x transitively on A1, and it fixes the point at infinity. So it has two orbits. This is a two-point set, which means there's two cusps. Oh, yes. Yeah. I mean, we defined what the set of maps were, right? Is things that have one GONS. So yes, I mean, if you're semi-stable, then you can build such a family. Yeah. Yeah, right. Right, well, I mean, I don't know how you would define what the right definition would be for that. Right, I mean, what kind of families would you want to consider? So you'd want curves where the fibers are what, like GMs or GAs? I just don't think there's like a good candidate for what you could want. I mean, the problem is that, I mean, if you think about what's going on over C, like, excuse me? Well, I mean, you want to constrain the genus of the fibers, right? But what do you mean generic fiber? I mean, you need to say what the C points are. No, but I mean, to define the moduli problem, you just have to say what it is over any base. And so, for instance, what are the C points going to be? I mean, you have to just add one point to the set, the normal set of elliptic curves, right? So what curve are you going to add over C? Do you want to use the nodal cubic, or do you want to use GA, or do you want to use another curve? Do you know what I mean? Yeah. I think that's just the problem. Like, the only possibly, definition that works is the one that we have. Yeah. I mean, it's related to the, yeah, I mean, it's just because, I mean, when you go up, what the special fiber is can change. So you have to kind of use what the stable one is to make things work out in the right way.
Construct them over every possible base.
Yeah, yeah. All right. So we said that there are two cusps. So x0n has two cusps. And this is for n prime. And maybe greater than 2, I don't remember. And they're called 0 and infinity. Because they're the image of 0 and infinity from QP1. All right, so that tells us that we need to add 2 points to y0n to get the right thing. So in particular, it's not going to be enough anymore, like what we were doing for m bar 1, to just consider one GONS, right? So the standard one GON has only one gamma 0 n structure. Again, if n is prime. Or I guess for any n, mu n, right? So if we only consider things that have fibers being one GONS, we're only going to add one additional point, so we can't get the right answer. So we have to go up to n GONS, right? That's the natural thing to do. So Cn has 2 gamma 0 n structures up to isomorphism. So it has mu n again, sitting inside the identity component, and it has the Z mod NZ. So that looks like what you'd want to use, right? But in fact, for technical reasons, you want your level structure to hit every irreducible component. So we'll see how that comes up in a minute. So what you actually want to use as the cusps are this guy and this one. So you don't want to allow this because the mu n doesn't hit each component. So this thing here is going to be the cusp infinity, and this guy here is going to be the cusp 0. So let me make a more formal definition. So m0 of n bar attaches to S, the groupoid of EGs, where E over S is a generalized elliptic curve, and G is a gamma 0 n structure, which in each geometric fiber hits each irreducible component. And that condition may look a little funny, but if you think about it, that means that that's equivalent to saying that the divisor defined by G is ample. It means you have enough points to embed this curve. What is the genus of y naught n? We wrote some formula before. It goes to infinity as n goes to infinity. Yeah. All right, so that's the definition. And so of course this condition, and this is for any n, not just n prime. And so this condition is going to, of course, bound what kind of polygons can show up, right? You can only get things with n sides or fewer. And so the theorem again is that this is a proper dm stack. So m0 n bar is a proper and smooth dm stack. Oh, yes, this is fine. Over z to n1 over n. And so all this stuff, compactifying these moduli spaces of elliptic curves by these generalized elliptic curves is due to Deligne-Rappaport. And so they have some very long paper that proves all these theorems that I'm stating. Okay, are there any questions? Oh, I didn't really get there yet, but we'll see soon. Like I said, it makes the G ample, which lets you do some things that you otherwise wouldn't be able to. Any other questions? It's like some closed subscheme, right? It's just, like think about a fiber, right? It's just like a bunch of points. Okay, so, well, here's one place where it's going to come up. So I want to talk about maps between these different m0n's. So suppose that, which way do I want it? N prime divides n. All right, so then the group gamma 0n is contained in gamma 0n prime. And so you get a map h star mod gamma 0n to h star mod gamma 0n prime. Of course, this is just x0n mapping to x0n prime. And we want to understand what does this look like in terms of the moduli theory picture. Okay, so on elliptic curves, it's very easy to see. So suppose that we have EG in M0n bar with E an elliptic curve. So G is a gamma 0n structure, so it's a cyclic subgroup of order n. So there's a unique subgroup of order n prime, right? And so the map just takes this EG to EH. All right, but it's a little weirder on the generalized elliptic curves. So suppose now that EG is just an arbitrary generalized elliptic curve. So we again have an H. Unique H inside G of the right order. But we can't just take EG to EH, right? Because there's this condition about meeting every fiber. And so the idea is just to contract the fibers that this thing doesn't hit. So I mean, if you think about one of these n-gons, some chain of p1s, and there's going to be a point of G in each one of them, H is some subgroup, so it'll maybe miss half of them or something. You just take the ones that aren't hit and just contract them away. And so the way that you can, and a nice way to actually do this contraction algebraically, okay, let me say, so let's say E bar be the contraction. So E with components contracted that don't need H. So the map takes EG to E bar and the image of H. Yeah. All right, so let me tell you how to actually, a nice algebraic construction of E bar. So let's suppose that F is the structure map from E to S. So you can look at the relative divisor, OE, and n copies of H, right? And you can take the global sections of this, and then you can sum over n to get a graded ring on S. So if you did this with G, since G is an ample divisor, if you take proj, you just get the original thing back, right? So now we're just going to take proj of this, and that's going to contract away the parts that H doesn't hit, because you only get sort of constant functions on those components. Okay, well anyway, that's the construction. Are there any questions? This isn't going to be terribly important for us, but I thought I should say it. So there's more details in doing rapport. Okay. All right, so now I want to turn to the topic of working over the integers. So far, whenever we've considered level n structure, n has had to be invertible. And that makes life a lot easier because it makes the n torsion a tau. Right? But now we're going to work over z. It's not going to be a tau. It's going to be harder to work with. Okay, so the basic problem is as follows. Well, I guess it's easy to say that elliptic curves in characteristic P can have no P torsion, or their P torsion can be too small if you think at the level of points. So for example, if he's in a supersingular elliptic curve, then the FP points of its n torsion are just 0. This is what happens when I try to write while I'm talking. The basic problem. Okay, so if you have a supersingular curve over FP, then we know that its p torsion vanishes, right? There's no p torsion at the level of points. And so what would a gamma p structure on E be? So normally it's 2 points that give a basis of the p torsion. But it has no p torsion, so there's nothing that you can do. I mean, if you use the normal definition, it just doesn't work. And so, I mean, if you use the normal definition, you'd just be omitting the supersingular points from the space, which is not good if you want something proper. And so there's a solution to this problem, which I think Drinfeld came up with. They're called Drinfeld level structures. They're a little more complicated. But fortunately, we can get around those since we're only going to need x0p or x0n. Okay, so you can do things like gamma p over z, but we're going to stick to something that's a little simpler. That's all we need. And I'm going to actually suppose that n is square free to do this. And I'll say why in a bit. Okay, so I'm going to define gamma 0 n structures again. So suppose that we have some generalized elliptic curve. And now S can be just over Z. So a gamma 0 n structure in E is a finite flat closed subgroup. It's a closed subgroup of E, which is finite and flat over S. And then we're going to define M0 and bar to be the set of these, I mean, it's going to be the category, the groupoid of these EGs, where again G meets each fiber. So, sorry, G meeting each irreducible component. And so the theorem is that this thing, M0 n bar, is a proper and flat dm stack over Z. So when n is inverted, this just reverts to the previous thing that we were talking about, and it's smooth over Z join 1 over n. But it's not smooth over the whole Z. And so we're going to talk about the special fiber and characteristic n in a moment, but I want to make some other remarks first. But question? Finite flat of order n. All right, so 2 remarks. So first, I'll talk about, well, n this square free condition. So you can do this with n square full. But there's 2 things to be aware of. So first, this definition isn't quite right in general, right? Because gamma 0 n shouldn't just be any subgroup of order n, it's supposed to be a cyclic subgroup of order n. So you have to make sense of what that means. So you need to define what it means for a group scheme to be cyclic of order n. Right? If n is p squared, should you allow alpha p times alpha p? Should you allow alpha p squared? You have to decide those kinds of things. So that's one problem. And when n is square free, everything can be regarded as cyclic. So we don't have to worry about that. And then a more serious problem is that if p squared divides n, then you can write down a generalized elliptic curve with gamma 0n structure that contains mu p in its automorphism group. And the fact about Deligne-Mumford stacks is that the automorphism groups are always a tau, which mu p is not. So this thing won't be a DM stack. But it is an Artin stack. So this actually works okay, I think, if you don't do generalized elliptic curves. If you're just doing the open moduli problem, then you get a Deligne-Mumford stack. But the compactified one causes problems. And actually, so I mean, Katz and Mazur worked out the theory of these Drinfeld level structures in a lot of detail in their book. And they didn't really do a moduli theoretic interpretation of the compactifications. They were just doing things like Y0n, but over all of Z. And then Deligne and Rappaport did the compactified theory, but they kind of didn't allow things at n. They were, for the most part, working over Z join 1 over n. And I think, like, working out, what happens in general, compactified over Z, wasn't actually done until like 5 or 6 years ago by Brian Conrad. I guess maybe because these kinds of difficulties come up. Okay, and the second remark is about the properness. So I want to say something about that. So the idea is the same, that you're going to use the semi-stable reduction theorem to fill in. So suppose that we have K is the fraction field of A, and we have some elliptic curve E over K with some G, a gamma 0n structure. So we want to extend the DVR and then fill in the elliptic curve and fill in the structure. So we may as well just assume from the outset that E has semi-stable reduction, because we can just go up and make that happen. And furthermore, we can assume that the underlying points of G are defined over K. So then what you can do is take the closure of G in the minimal regular model. So let me call E bar the minimal regular model. And I'll let G bar be the closure of G in E bar. And that actually lands in the smooth locus, because we know that the smooth locus is the Néron model and that all the K points of E extend into the smooth locus of the Néron model. This is in the smooth locus. And since it's semi-stable, the special fiber of the minimal regular model, well, it could be an elliptic curve, but if not, since we're semi-stable, it's going to be one of these n-gons. The Néron model, you remove the singular points and you get a bunch of GMs. But in the minimal regular model, you get one of these n-gons. I said that before when we were talking about the special fiber of the Néron model and the classification of them. So this looks like the kind of thing that we want. The problem is that this G bar, again, may not meet all the irreducible components. And so to solve that, you just do the same kind of contraction construction from before. So you just contract away the components here that don't meet G bar. And then you get something of the right thing, and that's how you extend. Maybe let E bar prime be contract components not meeting G bar. Then this E bar prime and G bar is n m0 n bar over A. Okay, so that's roughly how the valuative criterion goes. Are there any questions? Okay, so the last thing I want to talk about is what this thing looks like in bad characteristic. So we have this m0 n bar. If we worked over z join 1 over n, then it was smooth. So when you reduce it mod any prime away from n, you just get some nice smooth thing. So now we're going to look at what happens at n, where it's not smooth. So suppose that p divides n. We're going to stick with n being square free. We're going to let n prime be n divided by p. We want to look at this m0 n bar over fp. So first, let's think about what gamma 0 p structures look like in characteristic p. So suppose that we have an elliptic curve where k is an algebraically closed field. Characteristic p. So there's two possibilities for E, right? It can be supersingular or ordinary. So if E is supersingular, that means its p torsion is what? No, p torsion scheme. No. No, alpha p has order p. This is order p squared. That's the right answer. It's an extension of alpha p by alpha p. It's not alpha p squared, it's not alpha p times alpha p, and it's not the kernel of Frobenius on the second Witt scheme. It's the other extension of alpha p by alpha p. Okay, but the point is that it's a non-trivial extension. So it's only got one subgroup of order p. Of course, that subgroup's alpha p. Okay, and then there's the ordinary case. All right, so then what is the p torsion? Does anyone remember? So in this case, there's actually a p torsion point, right? And so over at p bar, that means there's a z mod p inside of it. And then remember that this thing is self-dual under the Weil pairing. I mean, it's its own Cartier dual. So if you have a zp, you also have to have a mu p. So it's z mod p times z p. And so there's exactly two subgroups of order p. There's z mod pc and there's mu p. And this mu p here is, you could also call the kernel of Frobenius. Let's say you can sort of pick it out. And this alpha p is also the kernel of Frobenius. Right, so if you had a group like z mod p times z mod p, there's a lot of subgroups of that order p, right? That's the lines in fp squared. But in this case, since these two group schemes are not isomorphic, you can't kind of do any kind of mixed thing. So you either get one or the other. That's why there's only two. So if you have some elliptic curve, there's actually a canonical gamma 0 p structure you can put on it, the kernel of Frobenius. And in the supersingular case, that's the only one. And in the ordinary case, you get one of the possible two. And so that suggests that there's a map from m0 n prime to m0 n, where you just add this canonical one. And so there is such a thing. And there's actually two maps. So there's another thing that you can do as well. So I'm going to define maps f and g from m0 n prime bar over fp to m0 n bar over fp. So it's going to work as follows. So suppose that we have some EG in here, where this guy here is a gamma 0 n prime structure. So then f of EG Well, this is going to be the obvious one that we just talked about, the kernel of Frobenius. So I take E, G, and then kernel of Frobenius. So remember, so E here is over some scheme S. S is just some FP scheme. And there's this relative Frobenius that goes from E to this twist guy. And then its dual is the Verschuebung, which goes from EP to E. And so one way to think about this E is that, well, at least away from the supersingular locus, you're adding, I mean, you have these two choices of the torsion group, and you're always picking the one that's not a tau. You're picking the multiplicative one. And so at a generalized elliptic curve, there's kind of two gamma 0p structures, right? There's the one where you use mu p and the one where you use e mod p. And here you're supposed to use the mu p one at the generalized elliptic curve. Okay, and then you can also, the other thing that you can do is you can, so g of eg is going to take, the elliptic curve is going to be this p twist here. And then I'm just going to take the inverse image of the group G by Verschuebung. So n is square free, so I mean, n is equal to p times n prime. So this Verschuebung is an order p map, so it's inducing an isomorphism on the n prime torsion. So you can just think of this as just kind of moving the g back along that isomorphism to some n prime piece, and then adding in the kernel of Verschuebung as the p piece. And the kernel of Verschuebung is this tau part. So in the ordinary places, this is adding in a z mod p. All right, so I'm also going to define two maps in the other direction. So we'll define f prime and g prime going from m0 n bar to m0 n prime bar. And so again, f prime is going to be the more obvious one. So it's going to take EGH. So this is your generalized elliptic curve. This thing here is a gamma 0 n prime structure. And this thing is a gamma 0 p structure. And what it does is just forget the gamma 0 p structure. And then g prime, it's going to be the less obvious thing. You quotient by h, and then take the image of g in that. All right, so we want to know what the compositions are. So if I do f prime and then f, so I start with EG, and then I add the kernel of Frobenius to it, and then I forget the kernel of Frobenius. So that's the identity. And if I do G prime G, I start with EG, and then I take this twist and sort of, I mean, the gamma 0 p structure I add is the kernel of V, right? And then to go back down, I'm quotienting by that thing. So I'm taking EP mod the kernel of V. So this thing mod the kernel of V. And V induces an isomorphism from EP mod its kernel back to E, right? And so G prime G is the identity as well. So if I do f prime G, that takes EG to this guy, and then just forgets about the kernel of V. And that turns out to be the Frobenius map on n0 n prime bar. And if I do G prime F, it's the same thing. So I first go to EGF, and then I'm killing the kernel of F. And Frobenius induces an isomorphism from E mod the kernel of F to EP. So this is again Frobenius on M0 n prime. And so, oh, maybe I shouldn't have erased those. Okay, so the idea is that every point here in the ordinary locus, it has two possibilities, right, for the structure that we put on, and F and G is kind of hitting, F hits one of them and G hits the other. And these are kind of isomorphisms. I mean, if you exclude the supersingular locus, these are isomorphisms from this thing to each piece, because these F prime and G prime provide inverses. And so the picture is that this thing is two copies of this. The supersingular points are glued. Right? And so I guess the result is that n0 n bar is two copies of m0 n prime bar glued along the supersingular loci in each one. And the gluing, I mean, so in each one of these two copies, you have the supersingular set, and you're gluing along the Frobenius map, because these compositions are Frobenius. And we'll come back to this, and I mean, we're going to talk about this. I think next time we'll do the Eichler-Shimura theorem, and this will be important, so we'll come back to it then. And this is also going to be important later on for something that we'll need to do. So it's very nice when n prime is 1. So you can do this at the level of coarse spaces also, so let's just do that. So in this case, m0 n prime is just p1. Right, at level 1, just the space of elliptic curves is the j line. And so m0 n, n here is equal to p, so it's prime. So if you look at m0 bar of p, in characteristic p, it's just two p1s glued at some finite set of points. Are there any questions? Okay, that's actually all for today. It's a little early.